Welcome to another week. So I'm sitting here at home getting ready for a wonderful day. I need to go visit a mall. That's what I am. Been to a mall. It's like mall weather. All this weather's actually pretty nice. So before I start, just a reminder for any of you who haven't subscribed, please subscribe. Again, it's free, doesn't cost you anything. It's something that helps me make these beautiful videos that people seem to enjoy. I may get a lot of views, so just subscribe. And I can also subscribe to your channel. Just let me know and I'll subscribe. All right, today we're going to talk about correlations and regression. And it's interesting. People use correlations to judge how strongly two things are related to one another, and often people misinterpret them for causation. Correlation and causation are not the same thing. When we get into regression, the next topic, both of which are being covered today, so this is going to be a longer type video. They're both being covered today. They're strongly related, and in fact, I'll show you how they're related, at least in terms of what's known as a simple regression. But we start doing regression because we want to control for what are called confounding variables. So sometimes you'll see the two variables are related on the surface, yet the reality is they're only related because of their shared relation with another third variable. We call that the third variable problem. That third variable is what is known as a confounding variable. Let's keep this in mind as you go on. So if people start talking to you about correlations and they get excited, you just have to temper their excitation. So with correlations, we're going to look at two types, the Pearson and the Spearman correlation. So with the Pearson, excuse me, correlation, each variable is continuous, meaning, or you can call it a quantitative, or you can say it's on an interval ratio scale. It's interesting. I was tutoring somebody who's taking a course somewhere in some university in Ohio, and her professor calls them numeric. So I mean, it's confusing, right, with all the terminology. As usual, individuals are a random sample from the population. We expect that, right? It doesn't always hold out. All these, when we don't meet these assumptions, our conclusions are often a bit off. The relation between the two variables is linear, so it should look like a line. I'll show you some examples of that. The two variables are normally distributed. They have a bell-shaped curve. We're also going to look at the Spearman correlation. The Spearman correlation is used when data are ordinal or continuous, so we don't have to have a continuous variable. And that does happen. So sometimes you might want to say you want to correlate answers on a survey question that's in an ordinal nature to another variable. So one is continuous and the other one isn't. The relation between the two variables is monotonic. It doesn't have to be linear. So see, this is not a line. However, what you required is this blue line here. So you'll notice that the blue line, this looks like I'm skiing down some really steep slope, and then it gets a little narrower. Actually, it reminds me of although it's not quite this steep, obviously, but Razor's Edge at Blue Mountain. You go down, and yeah. So, but you'll notice that you don't go back up, right, with the blue line. So that's monotonic, whereas that's monotonic cubic, whereas a true cubic relation, you'd go down and up again. So this presupposes the variable is monotonic. Correlate now in terms of so you have the two different options. There's also options available, and it starts getting confusing and to me, in my opinion, nonsensical when we're dealing with binary variables. Because with binary variables, I would prefer to use something different, like a chi-square, which we'll learn later, okay, rather than a correlation. But there are correlations for binary variables, or there are some too, right? So, but again, like I said, we'll use other kind of analyses to look at those. And those, by the way, those are called point biserial or biserial correlations. So if you ever hear those, they're referring to binary variables. Correlations range from 0 to plus or minus 1, right? The absolute value represents the strength and the sign represents the direction. So that's really, really important. So let's go back to the Pearson correlation. So this would be a positive correlation of a value 1.0, right? So, and I apologize for this being small, but you have these access to these data, to these nodes, you can expand. But the idea here is you'll see with a perfect correlation, the relation between the two variables, one is plotted on the x-axis and one on the y-axis falls perfectly on this line, the line that minimizes the distance between each point and the line itself. You have a perfect negative relation, you'll see it going down from left to right. So the not negative sign only means that the direction is negative, and here the positive means the direction is positive. The strength, the 1.0, refers to how closely these points are grouped together. So here we have a less strong relation. This is a positive of 0.9. This is a negative of 0.9. A couple of things here. You'll notice that it still has a general linear form, so you can draw a line right through this. It's not really curved, and it's minimal curve, but it's not really a curve. A line represents the relation really well here. 0.9 positive, negative 0.9. Here we have a 0.5 correlation that's positive and one that's negative. Still, you can draw a line perfectly through it. A correlation is a standardized covariance. So a covariance, so you should know this for the exam, because I think I do ask a question about this. What's the difference between a correlation and a covariance? The covariance, excuse me, is the same as the about that. Is the same as the variance, except for with the variance, this would be xi minus the mean times xi minus the mean, right? Because of that, the top can't be negative. But here, though, because we're looking at two different variables, we're not squaring, so of course we can have a negative value. So that when I say it's a standardized value, see we're dividing by the standard. We just divide the standard deviation of the covariance by the standard deviation of each variable. Okay. And you know from that first exam that I like to play tricks on you. Like for instance, that variance calculation, when I give you the standard deviation, I did that on purpose so that you didn't have to use the table. And some of you probably did use the table, but that was a little trick on my part because I wanted to make sure you're paying attention, right? So I could give you a table but also give you the covariances and the standard deviations. And some of you are going to still use the table when you have everything you need right there. There's a shortcut equation as well for the correlation, right? So this is just like the one we did for the variance. The only difference, of course, here is that we have the product of the standard deviations in the bottom here. These are variances, right? And then we take the square root of them to get the standard deviation. So everything's there. A term you should be familiar with. It's more important for regression than it is for correlation. The coefficient of determination, that's just the shared variance between the two variables. It's a square of the correlation, okay? So let's do one using the correlation data set and the equation for calculating Pearson correlation coefficient. Calculate the correlation between grade and depressive symptoms. So you have this access to this data set here. This is the data set. Wow, it's long. Luckily for you, Excel will allow you well, no, I'm doing it here for you, so you don't really have to do it. But I would practice it just for fun so you can understand how to use Excel. Because on the exam, you'll have stuff like this in the final. Oh, in the next exam, this one coming up actually this week. So here we have our variables. We're looking for the correlation between school performance or grade. That's what we have for school performance. The reason we have this is actually called perceived school performance because when you conduct research, getting things like grades is really hard, right? People are unwilling to share. So it's easier to get perceived, like how well do you think you do in school? Oh, I get A's, I get B's. I mean, people lie, obviously, but it's easier. I mean, how much do they lie? It's actually not, people don't lie as much as you think they would. But it's easier to get these data than it would be to get data on actual grades. So we have depression. These two variables, X and Y. See, I wrote everything out for you. What you don't have is the following, because we need all of these for that equation, right? If you look at the equation, Where is it? We look at the equation here. You need the summation of the x times y. Again, I suppress the x, the I equals 0 to n, right? Because we don't need that. Because now we're aware of that. We need to multiply x times y. So we need the sum of that. We need the sum of x, the sum of y. We need a lot of things. N is the sample size. We need to square the x's, square the y's. All right. So when you set up your program, you need to do all of that. So here's that's what I did here using all the funky Excel functions. I was able to get X, Y. I already showed you this stuff, so I'm not going to repeat it now. But anyway, so you have to set everything up appropriately, and then I use the dragging. Oh, wow, it's long, right? It's a long data set. Thankfully, Excel's really good at it. Kind of accelerates as you go down. So you get your x, sum of your x, sum of your y, sum of the x times y, sum of the x squared, sum of the y square. Then, of course, part of the equation is to take the sum of the x's and square it, the sum of the y's and square it, right? So I did all that stuff here. So you can see that. You can pause the video as you need to watch me do my magic. Okay, let's see. I think I did it right here for this one. Yes. Okay. So let's see. So we have so a lot of these things you see is 2023, so a lot of these equations haven't changed. It's not like there's been a massive improvement in technology and doing correlations and stuff. But the ones that you won't see that are older are the ones that I added to my textbook more recently, this new version that you have includes stuff like the Poisson and other stuff that you'll see later at the end of the chapter. At the end of the book. Okay, so here we have the sum of the x, y. So I usually just write down the equation and plug things in. Yeah, on the last exam, if you didn't show me, you could have showed me work, right? When you didn't show me work, if you were off on points, because you could type in work or you could paste. There's all kinds of ways to do things. And some students did, and I appreciate that. But if you didn't, how could I add points if you got something wrong? If you got to say, I don't know, on one item, if you got an 11 instead of an 8, I can't see where you did anything wrong. So that's just obviously wrong to me. So it's nice if you do show work. All right, so here we have our calculation. We just plug in all the data here, the sum of the x's, y's. I showed you all that. All right, just plug everything in. We get a negative 1.37. You should try this on your own and make sure you can get what I got. All right. So let's take a look at is it here? Partial correlation. So this is anticipating what we'll do in regression, because like I mentioned, there's third variables, the confounding variables, and we want to get rid of the effect of those thirds. So we want to partial that out. So this is what a partial correlation does. So in this case, it'll correlate two variables A and B and knock out the influence of variable C. The equation kind of, you can tell that that's what it's doing. So you're looking at the raw correlation between A and B minus the correlation between A and C and B and C, right? And in the bottom here, we're using the coefficients of determination, right, for those relations and removing that too. So let's take a look at how we do this. So basically what I need is I need correlations, right? I need yeah, I just need correlations pretty much, right? To do this, and then I do some squaring. So what I'll do is I'll give you these tables like this that have correlations. This is a prototypical correlation matrix. Now, this includes additional information. Generally, if you just had the correlations where they intersect, it's going to be 1 because this is the variable with itself. So this is a CESD is depression, right? So this is the correlation between depression and itself is 1. In a variance covariance matrix, rather than in remember, the correlation is a standardized covariance. In a variance covariance matrix, the diagonal will be the variable's variance. So we use the space, right? We tend to use stuff. We don't like to be inefficient. Interestingly, also, you'll note that, and again, there's a lot of extra information here, like there's significance and degrees of freedom. In a real, just a simple correlation table, what we generally do is just provide the correlation and of course, the ones along the diagonal. So it'll be perfectly symmetrical. Covariance matrix would be the variances in the diagonal. But it's symmetrical and it repeats itself. Above the diagonal and below the diagonal will be the same information. So often you'll see in a paper, on a published paper, that people will use one half of this, like the lower half or the upper half, to represent something else. You don't like to waste space, but that's how you read it. So here the correlation between depression and perceived physical appearance is minus 0.446. Correlation between depression and self-esteem is minus 0.692. So that's how you read this sucker. All right, let's go over here. So we got R A B dot C, where A is depression, B is self-esteem, and C is perceived physical appearance. So this, we want to see, does perceived physical appearance have any impact? Well, it turns out it doesn't have a great deal of impact, because our raw correlation between depression and self-esteem is 0.692, negative 0.692. They're inversely related. The higher depression, the lower the self-esteem. After removing the influence of perceived physical appearance, hey, I look great. Oh, I look terrible. It drops down to 0.593. So it's not much of a drop. Okay. Just make sure you do everything correctly. I mean, I know it's kind of a simple message, but you got to make sure you do everything correctly. Using the data in the following table, calculate the zero order Pearson correlation between self-esteem and perceived physical appearance. So I did those as well, and I'll include those in your data and your module. So the answer here is, wow, 0.647. I like to do 3 decimal places, 0.647, right? So that's the correlation between zero. We say zero ordered when we are doing a correlation, just a raw correlation. We're not removing, so it's not a partial correlation. This is just a regular bivariate correlation. So this is self-esteem and perceived physical appearance. So what's the correlation between self-esteem and perceived physical appearance? So we get 0.647. It's pretty high. Makes sense, right? All right, let's do the next one. So the next item is, and again, I want you to work on these, so I'm not going to go in depth over them. You're gonna do it yourself, right? A correlation between self-esteem and perceived physical appearance would make sense that it's positive. Sad though, right? Self-esteem shouldn't be tied to your physical appearance. That's my other self coming out here, my psychological self. Using the correlation in, this is SPSS output. By the way, in the exam, there were SPSS items. I didn't count those because I forgot to remove those, because when I wrote the book, we were still using SPSS. So I didn't even count those. You got them right. I just ignored them totally. And I know you did them, so you probably were able to look things up, and that's great, but I just ignored that completely. I forgot I have to change it to SAS. So that's maybe for third edition or something like that. I might just take out all computer stuff altogether. Okay, calculate the partial correlation between body mass index and PPA controlling for self-esteem. All right, so here we have body mass index. Here's the correlation, body mass index and perceived physical appearance, right? Controlling for self-esteem. So their correlation is minus 0.173. It's not that huge. We want to get rid of the effect of self-esteem. So let's go ahead and do that. Yeah, so it's not that hard to do. You just got to plug in the numbers correctly. It doesn't really change that much. It went from 0.173 to 0.153. So it's not a big drop after doing the control. This last one is a prototypical type question that I like giving. Given the means and standard deviations for BMI and self-esteem and their covariance, calculate the Pearson correlation. So again, knowing that the definition of Pearson correlation is the covariance divided by the standard deviation. All you need is this value divided by the product of these two values here. Okay. And that's what I did. But again, you need to know the definition. Okay. All right. Let's move forward. Let's talk about regression analysis. I'm going to write this down. What time is this? Oh, I don't know in the video what time. Well, I'm going to post it so you can hopefully click where it is. So in YouTube, you can click where it is so you know you can go from one topic to the other. Okay, so regression analysis is really cool. We're trying to make predictions, right? So we make these equations. So there, see, in a correlation, I was just correlating y and x, and we're not making a prediction. But here we're actually trying to predict the value of one variable based on the value of the other variable. So we have a simple line here, right? You have a line has an intercept and a slope, right? The slope is the gradient, right? The intercept is where the line crosses the y-axis. We have our outcome variable. Excuse me. And I don't know why I'm feeling like that today. I'm an asthmatic and sometimes things bother me. We have our outcome variable. You can use any variables you want, but become traditional to use y as the outcome and x as the predictor. So we have our outcome variable. You can call it dependent variable. I like to call it outcome variable. Y. You notice it has a little hat over it, so that means it's a predicted value. It's not an exact value. We're making a prediction. The I stands for the individual. Each individual in the data set gets her or his own predicted value. These B's stand for intercept and slope, right? They're parameter estimates. The intercept, I'll put a 0 here. You may also see an alpha sometimes. I think, in fact, here I use A and BX. So sometimes you'll have other values for the intercept or other symbols for the intercept. The B is the slope. The slope relates the predictor variable to the outcome variable in some way. Okay. So here I have x sub 1, indicating that probably in the future I'll have x sub 2, 3, 4 for other predictor variables. Simple regression, there's only one predictor and one outcome. And again, each individual has her or his own value of the predictor. You'll notice that there are no i's in the parameter estimates. It means they're shared by everybody. So they tend to be the same for everybody. That can be relaxed in more advanced statistics courses. Multiple regression, you have more predictors. So here you can have as many as you want, but one of the rules about modeling in any kind of modeling is that you want to make it as simple as possible. So if you have a lot of predictors, what you'll do is you'll increase the R square. The R square, we talked about that earlier, the proportion of the variance accounted for in the dependent variable, the outcome variable. But the model becomes really messy and it becomes useless. So if you can predict, say if I could predict my outcome with only one variable, I am gold, right? The more variables I use, the less useful the predictor is. So we try to limit the amount of predictors to the least number we need to get the best prediction. Okay, so these are prediction equations. So let's look at how correlations are related to our coefficients, the regression coefficient, or slopes. So the relation is, by the way, if you hear me say relation, remember, I think I've mentioned this before, relations are for people, relations are for variables. So B, that's our slope, just the general B. But we're talking about, again, here I'm talking about simple regression, okay? So B is equal to R, so that's a correlation between the two variables, times the standard deviation of the dependent variable divided by the standard deviation of the predictor variable. Okay, we'll probably put these in just to make sure. Yeah, I put these in parentheses of some sort. Okay, just so you know. So let's go ahead and calculate a regression equation by hand. Okay. So again, here's a prediction equation. Again, I mentioned earlier that I'm going to change the symbol sometimes. So we have a plus bx. There's no b sub 0. And in fact, I should probably have a little sub I here just to keep. I can't see my little scale. My stuff's here, but there should be a sub I here too. Let's keep that in mind. All right, so I just need to isolate the A, so I'll just rearrange this so that my A is on the left side. But basically what I'm doing is subtracting bx from both sides. So I get A equals y minus bx. But because I don't have the y and the b value, what I use the best estimate of an outcome absent all other information, and that's the mean. So I use the mean of y and the mean of x, and then I can go ahead and calculate my my variable. Okay. So here's an exercise. Write the regression equation. These are old data. I love it, though. It's really shows how horrible life was in the past. Okay. Write the regression equation for the following data with per capita cigarette consumption in 1930. That's our X variable predicting incidence. Incidence is an epidemiology term that means the number of new cases of lung cancer, and we usually express it in some number like per 100,000, per million, per 10,000, whatever. Also interpret the effect. So here's our mean cigarettes, mean lung cancer cases, standard deviations, and correlation. So I can use all this information and write my prediction equation. So we calculate our slope, right? The correlation times the ratio or the ratio of the standard deviation of y to standard deviation x. We just plug in our values. We get 0.0228. Calculate our intercept. Again, we use the means of our variables. We get 6.787, and we write out our equation. So here we're predicting cases of lung cancer based on per capita cigarettes. The important thing with regression is knowing how to interpret it. So let's do the interpretation. Each additional cigarette smoked per person. Remember, our X was per capita, this number of cigarettes smoked per person, which was insane. Like in USA, there were 1,300 cigarettes smoked per person in 1930. It's crazy, right? On average, right? So we're looking at each additional cigarette smoke per person in 1930 was associated with a 0.0228 increase in the incidence of lung cancer per 100,000 population. So that's how you'd interpret that. So you have to know one thing about regression is you have to understand the scales. When we use these what are called unstandardized values. So everything has to be reported in scale. I'll talk to you about standardized values in a moment. Cool. So using the data in the two tables, write the regression equation to predict physical activity support from physical activity enjoyment. I'm going to let you practice this since we did this already, and I gave you the answer right here. That's what it should look like. You should get that answer. You can do it on your own. All right. Let's look at regression assumptions. There are certain assumptions that go along with regression analysis. One is we have linearity. So we're looking at a linear relation between the predictor and the outcome. So this is a line. Now, you doesn't have to be linear. I mean, you can do cubic, quadratic, whatever type of relation you want, but that's a little bit different. Okay, talking about linear regression here. Simplest model is always the best model. Linear model is better than a quadratic or cubic if it works. It's simpler, right? Independent observations, normality at each level of x. I'll show you that in a second, and equal variances at each level of x. So this is what I mean by that. So x is your predictor, y is your outcome, and x has different levels to it. In some cases, now one thing about regression is outcome has to be continuous with linear regression, right? But your predictor can be anything. It can be a count, it could be some ordinal variable, it could be a nominal variable, whatever. Like if you had an ordinal variable where there's one, two, three different levels, you'd expect to have normality distribution of y at each level of x, right? That's what this means here. Now we can't look at in the model, we can't see the y, right? After the model's created, the way we look at it is through the residuals, through the leftover stuff that wasn't predicted by our models. We're generally looking at our residuals here. And when we talk about equal variance at all levels of x, we're expecting the variability to be the same, right? That's sigma here at all levels of x. We call it homogeneity of variance. So when we talk about multiple regression, we're still doing the same kind of interpretation, right? And we're talking about non-standardized values. Because we can standardize these values as well. And you'll see this in output, you'll have standardized and non-standardized outputs. So let's look at interpreting a regression coefficient. Each unit increase in x results in a b change in the outcome, right? A b, whatever b is your slope, right? That's the way I interpreted the last result. Sometimes we standardize values. Now, the reason I would standardize value is if I'm interested in making comparisons, like which of these variables has a stronger effect on my outcome. When I look at unstandardized values, it's hard for me to do that because they have different scales. So I have to be able to match the scales. If we standardize the values, we can. So we'd say each standard, so you'll get standardized and non-standardized coefficients, regression coefficients, B's. If I have a standardized regression coefficient, we'll say each standard deviation increase in the predictor results in a B standard deviation change in the outcome. So we talk about terms in terms of standard deviations. And now we can have a direct comparison to see which one has a bigger impact on our outcome variable. Pretty cool, huh? One thing you never want to forget, though, is to mention that when we're interpreting our results, we're holding all other variables constant. And this is what we call statistical control. It's like we're interpreting the effects of each of these predictors on the outcome, right? And this prediction. So here's the prediction equation with a hat. So when we're interpreting this result, these results are based on these variables being held constant, like at the mean for everybody. So we look at one variable at a time. So that's why we always say holding all other variables constant when we're doing a multiple regression. Multiple regression means you have more than one predictor variable. All right, let's talk about diagnostics and regression. First thing we want to do is check for outliers. Outliers are cases that are extreme in one way or the other, right? So we can look at outliers through the the residuals. Now, so it's important for me to distinguish between the two models that we saw before. One was the prediction model, right? And then one is the true model, just the real model that we're using, right? When we're doing regression, we already have the data. So our data include our outcome and our predictors. So I can test how well my prediction model predicts my outcome. The way I can do this test is by comparing the predicted value to the actual value. So if I take the predicted value and subtract the actual value from it, I get the residual. So these two equations are related by this residual. So the residual is the difference between these two equations. So the prediction doesn't have any error. It's just a prediction. It only has an error when we compare it to the actual value, outcome value. And that's what our residual is. And again, it has an I, right? So it means that each individual has her or his own residual. So what do we consider an outlier? Well, it's up to you as the researcher. We tend to say 3 standard deviations from the mean. So if a standardized residual is greater than three standard deviations from the mean, we would consider it an outlier. So three standard deviations, if you recall that empirical rule, we have 95% of all individuals are within plus or minus two standard deviations of the mean. 2.5% are out at each end. That's why a lot of you got that item wrong on the exam. It's 2.5% are outside the two standard deviation mark. A lot of people put 2.28 for some reason. Uh, so are outside of the two standard deviation mark. But if you go to three, it's going to be a lot less, right? So we're just trying to be very short. Now, what do you do with those residuals? I mean, some people like to get rid of them, get rid of those cases, but in data collection is expensive and it costs a lot of money to collect data. It takes a lot of effort to collect data. And especially when you're not dealing with giant samples size, you don't want to get rid of data or cases. So we try to avoid doing that. So we try not to. So we have to investigate those outliers. And there's many ways to look at them, and there's way beyond the scope of this course. But there's many ways to look at them. We also want to check for multicollinearity. Multicollinearity means that the predictors are strongly correlated to one another. We'd like each predictor to count for a separate proportion of the variance in the outcome. And that's really important because if two variables are strongly correlated, the correlation is 0.9, that means they're basically saying the same thing, right? So why would I want to include them? We want unique predictors, right? One way we can check for multicollinearity is by looking at the tolerance. That's the proportion of variance of a predictor that's not accounted for by the other predictors. So basically, we're doing a regression of one predictor on the other predictors, right? That's not accounted for by the other predictors. Okay? So that's the tolerance. The VIF is 1 divided by the tolerance. So you get both of these statistics in general. Here's the heuristics. Values for tolerance, values less than 1 are troubling, again, because it's the proportion of the variance not accounted for, right? So we'd like high proportion not being accounted for, right, by the other variables, and then VIF values greater than 10 are worrying. And it just makes sense based on this equation here. We want to look at homoscedasticity. So we want to look at the spread of the variance, um, at different levels of the predictor variable. And we can do that by plotting the standardized residuals versus the standardized predictors. Yeah, I'll show you that in a separate video on how to do a regression. And the coefficient of determination is the total amount of the variance in the outcome that's accounted for by the predictor variable. So again, in a separate video, I'm going to show you, I'll run a regression analysis and we'll discuss that. But for right now, this is what you need to know about regression and correlation. I'm just going to add one couple of last things here. Historical stuff. I'm not a big fan of Carl Pearson, who's known for the Pearson correlation and also for the Pearson chi-square, because he was a eugenicist. So he didn't believe in, he had some nasty beliefs. He was the head of the Eugenicist Society. And I don't know if it was international or in England only, but he was not one of my favorite characters, and I hate that we have to name things after him. And this guy was actually praising Adolf Hitler to see if he could do good work in alleviating the world of, people who didn't deserve to live. And I feel sad that we name things after him. So I'm not a big fan of Carl Pearson, but this is what it's named for. I wish we could change that. Somebody maybe will. I don't know. Let's see what else. Yeah, the other reason, another one I went, these are just interesting things. The reason I use heuristics instead of rule of thumb, some of you may already know this. The rule of thumb had to do with the size of a switch or a stick that a man could beat his wife with. So I think that's a kind of, we shouldn't be using that term. I know people differ on this And that's you, that's me. This is the way I feel, so I use heuristics rather than rule of thumb. But sometimes when I have to look things up, because most people still use rule of thumb, I'll look it up that way too. Can't control for what other people do. All right, thank you, everybody. Enjoy.